Good morning, grade 8 students. Today we are going to continue the last section, electric currents from magnetism. Last time we talked about electromagnetic induction. We said that whenever we have a wire, okay, and you have a magnet, a loop of wire, and you have a magnet that you move it in and out of this loop, here you will cause the charges which are at rest, which were at rest in this magnet, to move. Okay, so we said if you connect a wire to galvanometer, why here we connect to galvanometer? Because this is the device that tells me if there is a current or no. This is the device that detects the current in the circuit. Okay, so if we move the magnet inside the loop, we can see that the needle of the galvanometer deflects, showing that there is a current flowing in the circuit or in the loop of wire. This is like the first case here, A. Part B, here when you keep the magnet at rest, you see that the needle returns directly back to zero. You keep it at rest outside or inside the loop, it doesn't matter, okay? But if the magnet so at rest, okay, it means that the current is zero, no current. The charges at rest, not moving. When you move the magnet out of the loop, you will see again that the needle will deflect to the opposite direction, showing that there is a current flowing, but how? In the opposite direction. Okay, now girls, we said only when the magnetic field through loop is changing does a current flow through the loop. So here we can get a conclusion that when the magnetic field around the magnet changes, there is a current. Here, when you move the magnet in, you are causing the field lines which are around the magnet, this region that we can't detect it in eyes, it's a region that surrounds a magnet, okay, this region changes, okay, you are moving it inside the loop, so you are causing the field lines, these blue field lines, to change. So we can conclude that when the field lines or when the magnetic field changes, there is an induced current. Why it's called here induced current? Because it's produced by this magnetic field. There is no source of electricity, no power supply, no battery, nothing that giving current or flow of electrons. Okay, so this flow of electrons or current is produced by the change of the magnetic field. Here, when you keep it at rest, the magnetic field is not changing. The field lines, they are not changing. The number of field lines that enters the loop is not changing, so no current. When you move the magnet out, the number of field lines changes, so you have current. So conclusion, whenever the magnetic field changes, okay, in a loop or around a loop of wire, around a wire, the charges in this wire, they will begin to move. Why? Because when this magnetic field change, here there is a magnetic force, there is a force exerted on these charges inside the wire, causing them to move, so to give what? To give current, because current is the flow of electrons, of electric charges. And faster the movement, the more current. We said this the last time. Current changes direction when either motion is reversed, like in and out, like here, or when polarity of magnet is reversed, when you, for example, enter the south pole instead of the north. So we talked about this the last time. Okay, so when a magnet and a wire move relative to each other, a current is induced. Relative motion is needed. So it means relative motion. It doesn't matter which one moves, the magnet or the wire. Okay, maybe here, I will show you in another slide. Maybe the magnet is at rest and you are moving the loop in and out of the magnet. Okay, or the loop at rest and you are moving the magnet in and out relative to the loop. So it doesn't matter which one moves. The most important thing is to have a relative motion that causes the magnetic field to change. Okay, the effect of producing induced current is known as electromagnetic induction. Electromagnetic induction can occur by moving a magnet into and out of the coil, which causes the charges to move, therefore to have current. Moving the loop into and out of the magnetic field of the magnet in a direction that's not parallel. Okay, I will talk about this note in later, okay, in the next slide. Or rotating the loop around the magnet or around the magnetic field of the magnet. So therefore, current is induced as long as the magnetic field is changing relative to the wire. What means magnetic field is changing? It means these field lines that are around the magnet are changing. Okay? Here, another note. Now, here girls, you have loop, but as you can see, here I have 2 turns, here I have like 4 turns, here I have like 6 turns, okay? But the same effect here is produced. I have electromagnetic induction. Why? Because I am moving the magnet in and out of this coil, in and out of this coil, in and out of this coil. So when I move the magnet in and out, okay, revise now girls the concept in your mind. When I move the magnet inside and outside of the coil, the magnetic field around the magnet will change, causing the charges in the wire to move. It means producing what? Producing current. This is the effect of electromagnetic induction. Okay, so now because of this relative motion, because of this motion of the magnet in and out, I got current in the coil. I got current. Okay. Also revise with me in your mind. When you have current in the coil, what we learned in section 2, when I have current flowing, this current now produces magnetic field around the wire, right or no? This is what we learned in section 2. Whenever I have current around this wire, this loop, this coil that has current, I will have what? Magnetic field. So imagine now I have the magnetic field of the magnet plus the magnetic field of produced by the coil that has current. Okay, so it's like 2 magnetic fields against each other. It's like when you put 2 magnets it's like the effect when bringing 2 magnets near each other. They will like push each other, right? You will feel the force exerted by them. So it's more now. What is the note here? The note here that it's more difficult to push the magnet into a coil with more loops. Why? Because more loops, it means here the greater the magnetic field around this loop produced by the current in this loop. So the greater the interaction between the magnetic field produced by the loop and the magnetic field of the magnet. So that's why it's difficult, more difficult. So it's more difficult to push the magnet into a coil with more loops because the high current generates a stronger magnetic field which acts again the magnetic field of the magnet. Okay, so it's a easy concept. You have just only to arrange the ideas in your mind. Okay, so first, when you move the magnet in and out, you create current in the loop. This current by its turn creates magnetic field. So the magnetic field, I have now magnetic field that it's interacting with the magnet, with the magnetic field of the magnet. Okay, so more loops, more magnetic field produced by the loop, so harder to push the magnet in and out because the stronger magnetic field acts against the magnet. Okay, this is only the note for this slide. Now, so the strength of the current produced in a coil by electromagnetic induction depends on the number of loops. If you increase the number of turns, the number of loops, here the current will be stronger. And the strength of the magnet. If you use, girls, a stronger magnet, okay, so for sure you are going to make more charges move in the wire. It means you are going to get higher current. Okay? Electromagnetic induction produces now electrical energy, but energy is required your muscles for electromagnetic induction to work. Pay attention with me. All of you know the conservation law of energy. We all know that energy cannot be created from nothing, right? Okay. Now, electromagnetic induction, this effect states that the current is induced in wire because of the change in magnetic field. Okay? Because of the change in magnetic field. So, what means current? It means electric charges that are moving. So type of energy is electrical energy. So if this electrical energy, girls, here, like coming from nothing, created from nothing, I have a wire and I got like suddenly a current which is moving or flowing through it? No. So if I say yes, this means that the conservation law of energy is wrong. Because the conservation law of energy states that energy cannot be created from nothing. So this electrical energy in the wire, okay, is coming actually from the energy of my muscles because I pushed the magnet in and out of the coil. Okay, so here this energy is transferred to the electrical energy. So for sure always energy changes form, cannot be created or destroyed. This is the conclusion for this part of our lesson. So an electric current can be produced in a circuit by changing magnetic field. This one you have, okay, it's only one sentence, but you have to understand deeply. Okay? This can be accomplished how? By changing the strength, position, or orientation of external magnetic field. It means like by moving a magnet in and out, like this, you are changing the position of the magnet. By using a stronger magnet and move it also in and out, by, for example, turning a loop, by moving the loop. Okay, you have all the details in the previous slides. Now, here, I told you before that when we move the magnet in and out of the loop, we have to move it not parallel to the magnetic field. Why? Pay attention with me. Let's say that I have this wire, this is the wire, okay, and I have here a horseshoe magnet. A horseshoe magnet. You know the horseshoe magnet. Okay, so horseshoe magnet, it has this shape. It has one north and one south. Okay, and the wire is inside. Okay, so did you imagine the situation? I have here a rounded horseshoe magnet and the wire is inside. When the wire in a circuit moves perpendicularly to the magnetic field, see, the magnetic field, the field lines are going, let's say that here north and here south, okay? So horseshoe magnet from here to here, okay? And the field lines, the blue lines, are going from north to south like this, okay? And you are moving the wire how? In and out. So here you are keeping the magnet at rest and you are moving the wire in and out. In and out, okay? So see, this yellow arrow shows the motion of wire. So in this case, you are what? You are crossing the field lines. The field lines are what? Are parallel. The field lines are the blue lines. When you bring this wire and you move it in and out, you are crossing the field lines, you are changing the magnetic field. It means here the charges in this wire will be able to move because I have a change in magnetic field. Okay, so electromagnetic induction current is induced whenever the magnetic field is changed, simply. Okay, so whenever the magnetic field changes, you have current, you have flow of charges. So here, when you move the wire up and down, you cross the field lines, you change the magnetic field. So field line changes, so magnetic field changes, so you have current. So how the wire here moves? It moves perpendicular to the field lines. Field lines are like this, the blue, and the motion of wire yellow, up and down. Okay, when the wire moves perpendicularly, so here the field lines are changing, so I have what? Current. But here the same thing, I have this horseshoe magnet, north and south, the field lines are going like this, parallel, blue lines. And here let's say that you are moving the wire, how? Also back and forth like this, along this yellow arrow or direction. In this case, you are moving the wire with the field lines, you are not crossing them. You are moving the wire with the field lines, so you are not causing here the magnetic field to change. So since the magnetic field here doesn't change, the charges won't move, so no current. So that's why in the previous slide here I told you moving the loop in and out of the magnetic field of the magnet in a direction that is not parallel, because if you move it in a direction that is parallel, no current will be produced because there will be no change in the magnetic field. I hope that it's clear. So when the wire in a circuit moves perpendicularly to the magnetic field, current induced in the wire is maximum. But when the wire moves parallel with the field lines, no current, because no change in these field lines. So there is only magnetic force on the charge. What causes this charge to move is the magnetic force exerted on them. Only on a charge that's moving how? Perpendicularly to the direction of magnetic field, like this case. Okay, so watch with me this video, it's very important.
Electromagnetic induction. Prepare a circular coil out of copper wire. Connect the two ends of this coil to the two terminals of a sensitive galvanometer with a scale having 0 at the center. This closed circuit is shown in the diagram. Note that this circuit contains no source of electricity and the galvanometer shows 0 reading initially. Take a bar magnet NS and move it swiftly towards the coil with its north pole facing the coil. You will observe a deflection in the galvanometer when the magnet is moving. The deflection indicates that current is set up in the coil. Now, move the magnet away from the coil. The galvanometer shows again a deflection, but in the opposite direction. This means current is set up in the opposite direction. If you hold the magnet with its south pole facing the coil and repeat the above steps, the deflections are again observed, but are reversed. Similarly, motion of the coil itself also produces deflections in the galvanometer when the magnet is kept stationary. Do you observe any deflection when you just hold the magnet stationary near the coil at rest? No. A relative motion of a magnet and a coil induces the current in the coil. The current produced by a relative motion of the coil or the magnet is called an induced current and is said to be set up by an induced electromotive force.
Okay, till here it's enough. Okay, the last part for today, it's about generators. Now, generators, it's a word that you hear about it. For sure you heard about it before, right? Generator, from its name, what does it do? Generators, what does it generate? Why it's called generator? Because it generates electricity. It gives electricity. From where? Where does it give electricity from? We know that always we have a conservation law of energy. Always the energy is transformed from form to another. So this electrical energy given by a generator, where is it coming from? It's coming from mechanical energy. So a generator converts mechanical energy into electrical energy. So if you focus in this sentence, it's the opposite of what? It's the opposite of electric motor, the one we learned about it in section 2. For electric motors such as the fan, we said the fan, it takes electrical energy from the outlet and it gives us what? Mechanical energy of the blades. The blades move. Okay, so we said that the electric motor, it changes electrical energy to mechanical energy. But here, when we say generators, from their names, they generate electricity. Okay, so they convert the mechanical energy to electrical energy. A very easy example. You will see that all the generators, they have this method. Okay, we have like a magnet, like a horseshoe magnet, and we have inside this magnet loop of wire. Okay, and this loop of wire, let's say here it's connected to the wires that I want to induce current inside them. Okay, here I have wires, and these wires I connected to any device such as lamp. Okay, I have this loop of wire. Now if I rotate this loop of wire, you are rotating it, you are changing the position of this loop inside what? Inside the magnetic field of the magnet. So here magnetic field lines, they run from north to south. So when you rotate this yellow loop inside this magnet, you are going to change, to cross these field lines, you are going to change magnetic field. And we learned, according to the electromagnetic induction, that whenever magnetic field changes, there is an induced current. So when you rotate this loop inside the magnetic field of this magnet, okay, current will be induced inside, and so charges will move, current will move, and when current moves through the resistor or the filament of the lamp, what happens? The lamp will glow. Okay, so simply we can generate electricity by just using this simple way, okay, by using a mechanical energy. So here the mechanical energy, the motion, the mechanical energy of the loop, it's converted to electrical energy. Okay, so girls, in our everyday life, the electricity in our homes, the electricity around you, like if in the outlets in your home, it's what? It's coming from where? It's coming from a giant power plants, and these power plants, they use generators. Like you have hydroelectric power plant that uses the water. We have a coal power plant. It is the most common one, that burns the coal in order to give steam. Okay, then this steam, what does it do? It turns, there is here turbine. This turbine, when the steam passes through this turbine, the turbine moves. Okay, moves, so rotates. Okay, rotates. So this turbine that rotates is connected to what? As you can see, to a loop of wire, to a loop. And this loop, where is it placed? It's placed inside a giant magnet. So when this loop rotates inside the magnet, what happens? The magnetic field of this magnet changes. When magnetic field changes, current is induced. So current flows in these wires. Therefore, we get electrical energy. And this electrical energy is therefore transmitted to our homes, to our offices, to our schools, of everywhere. Okay, a turbine. So this turbine, when the armature of a generator is connected to a wheel, it's like a wheel which captures, it maybe captures wind, maybe water, maybe steam. Okay, so in order to turn and produce electrical energy. So here it depends on the type of the power plant we have. Okay, we have, girls, power plants called hydroelectric power plant. Hydroelectric power plant is, it uses the running water. They build like dams, and these falling water, they direct the falling water against the blades of this turbine. Okay, so when the water, the falling water, passes through the blades of the turbine, it causes it to turn. And the same thing, the turbine is connected or attached to what? To loop, or a core wrapped with many loops. And these loops, they are rotating where? Inside a strong magnet. And the result is what? Electrical energy. So this is one type of power plant. Another type of power plant, coal power plants. They use the energy produced by burning fuel. So they burn the fuel, and then this energy coming from burning fuel, it converts water to steam, and therefore the steam moves through the turbine, and also the same thing causes the turbine plates to turn, causes the loop to turn. Where is the loop? The loop is placed inside the magnet. So the magnetic field changes, and the result is electrical energy. Third one, nuclear power. Fourth one, we can have also wind power by using the energy of the wind, geothermal power also, and solar power by using the energy of the sun. Okay, so this is everything for generators. But here I want you also to know that the electrical energy we get from generators, it's not always in one direction. Girls, I'm sorry, where is it? Here. Okay, here when you rotate the loop, okay, you are creating electrical energy, but this electrical energy, it's not only in one direction. Not always, for example, the current is moving from this side to this side. No. Why? Because here you are rotating a loop inside a magnet. Okay, and we said if the loop, for example, if the wire is parallel to the magnetic field, no current will be produced. Okay, but if it's not parallel, there will be current, and the current produced, it depends also on the orientation. We can say simply on the orientation of this loop inside the magnet. Okay, so actually, girls, every half rotation, when we rotate the loop inside the magnet, every half rotation, the current changes direction. If it was moving from here to here, it will move from here to here. Okay, so all generators, they produce the same type of current, and this current we call it alternating current. Why it's called alternating current? Because it alternates direction every specific time, every specific interval of time. Okay, so the electricity now that you have in your homes, in your office, in the offices, everywhere, it's an alternating current. It's the current coming from this electricity, it changes direction every like a specific interval of time. It's not like the current coming from battery. You know, when you put a battery in a specific device, okay, the current, the electrons will flow from the negative side to the positive side, always in the same, in one direction. Okay, so the current